Okay, so here's the basic premise for problem number 6. We have a baseball being pitched at 32 meters per second, comes in, hits the batter hits the ball and pops it straight up into the air. They give us the idea that the ball will go up 36.5 meters from the point of contact, and then from there they're asking us if the ball was in contact with the bat for 0.0025 seconds. Just what is the average force acting on the ball by the bat during that collision? That's all that's given to us. So the way that we'd approach this first is that we need to determine the velocity that the ball receives after the hit, and that's just a simple calculation working with energy conservation. So it starts out here with kinetic energy after it leaves the bat. We want to figure out what its velocity is right after it leaves the bat. So when we go through and set the 1/2 mv squared equal to the mgh that it acquires, and you solve that, you're going to get the velocity after the collision is just the square root of 2 times g times h, which is 26.7 meters per second. So now we have enough information to be able to solve for the amount of force acting, and we're going to use the idea that we're going to use the impulse momentum theorem, essentially, that says the net force acting over a time interval is equal to the change in momentum that the ball experiences. So a pretty powerful theorem. In this case, the time interval is so small that it makes sense to use the impulse momentum theorem, because it's so hard to measure that time interval. Forces and accelerations are really hard to calculate here, so we're just going to go ahead and loop them all together and call that the impulse that's being delivered, and that's equal to the change in momentum. Since they're asking for the magnitude of the force that's acting, we'll just solve that equation for force, and so we need to look at the change in momentum that the ball experiences and divide it by the time. So how to do that? We have to take care of vectors, and if we take a look at the initial vector being 32 meters per second, let's use the right color here, 32 meters per second this way, and the final velocity being 26.7 meters per second this way. So if we look at, again, the initial velocity being 32 meters per second, final velocity being 26.7 meters per second, what we would like to do is now determine the magnitude of the change in momentum, or we can even just determine the magnitude of the change in velocity. So the way that we're going to do that is we're going to take this thing and point it the other way. We're going to take that, make that be a negative v initial. So I'm just going to go ahead and swap that direction and make that be a negative v initial, and then take it and add it to this. So now what we get is v final minus v initial. This is the magnitude of the change in velocity. It's going to go the other arrow. It's going to go this way. That's the magnitude of delta v, the direction of delta v as well. So what we want to do now is we just want to determine what that size is. To be able to do that, we have a right angle here, since we had the initial velocity being 32 towards the right and the final velocity being straight up. So we can go ahead and solve for this using trigonometry. And what we get when we do that math is that we get that the velocity, the delta v rather, is about 41.7 meters per second, and at an angle. And that angle can be found probably using the arctangent function. So let's go ahead and just calculate that quick. And what we get for theta, when you take the arctan of 32 over 26.7, is we get theta to be about 50 degrees. So roughly 50, maybe 50.2 degrees. Now that's the change in velocity. So I'm going to go ahead and go back up to this equation here and say that's really m delta v all over the time interval. Well, the mass of that ball was 0.145 kilograms, and the change in velocity was a 41.7 meters per second, and so that would be the magnitude of the change in momentum. I'm going to divide that by the time interval, and when I do that, what I get is the average force that's been acting on that ball. And that value is about 2,400 newtons. about 2,400 newtons, and the angle would be at 50 degrees from the vertical. And so that's how you can use the impulse and momentum theorem. You do have to remember that momentum is a vector, and you do have to remember how to take a change in a vector quantity. So notice how I took the v initial, I changed the direction of it, and then added that to v final to get delta v.